is an overview of WebGL. I promise it's not going to be very hardcore. The main point of the presentation is to give you a good idea of what is suitable for and how is it better. So my name is Denis Radin. You can find me as a Pixels Commander online. I work in a company called Focus Reactive. We are doing a software house, also doing some 3D projects. Now I'm busy with a big 3D project migrating from Babylon.js to React 3 Fiber. I work with computer graphics for quite some time. I started in 1991 with the ZX Spectrum. It was a funny system. Maybe some of you had this kind of computer with 4 colors, and then the graphic system was very weird. You can put only 2 colors on an 8 by 8 pixel screen cell. Then I was working with the Delphi and DirectX, and in C# was developing vector engine, and then had a lot of fun with Flash, with 3D games we've been making. That's a long demo. Then I made my HTML5 canvas game engine, one of the first in the world. I was making some games with that. Since 2013, I was working for the biggest. Oh wow. That's yeah, quite some difference. So since 2013, I was working for biggest internet provider in the world, Liberty Global. We've been developing operation system with WebGL, React. It was a very fancy project, but the problem was hardware. We spent 4 years tuning performance of our application, of our UI, and we used WebGL for that heavily. But yeah, we had quite some fun with that, and since June 2017, I joined a WebGPU working group. It's a public group, you can join as well. I was observing all the changes. So in this talk, I will tell you why do we need WebGPU, what's the history of its appearance, how is it different from WebGL, how is it better than WebGL, and what it brings us, what are new capabilities that it empowers developers with. Why do we need WebGL, WebGPU at all? This is because we need parallel calculations for graphics, and just for intensive calculations, we need them to be done in parallel. Who've seen this video? 4 people out of the whole. Okay, this video explains the difference between CPU and GPU. Yeah, am I muted? No, I'm not.
In the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1.
This is a CPU.
Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into
now
all
the
1,100 of these tubes,
branded
into these
GPU.
tubes, in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space, and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
Amazing, guys. Really nice explanation of the difference. So yeah, the difference is that on GPU makes calculations in parallel, and we need another API. We can't give instructions in imperative way, step by step, but we need another API for that. So what's WebGPU? This is a new API for graphics and computations. This is important because WebGL was an API only for graphics. WebGL was a direct port of OpenGL API, and WebGPU is developed from scratch, so it doesn't have any ancestor in some native development, game development world, whatever. Oh, what's wrong with WebGL? We started somewhere from there, and now we are where we are. I'm not sure how many people play computer games, but 3D graphics changed a lot. And all approaches changed a lot, and requirements also evolving. OpenGL, which is the actual interface on a driver level for WebGL, it takes its roots back to 80s. It's a very old API. The first version of OpenGL is from 1992. It's almost 30 years. I'm pretty sure there are people who are younger in this hall than OpenGL. But during the time the first WebGL prototype was rolled out, it was still quite a cool thing. There was still some promise from OpenGL, but then things went wrong. Drivers on both desktop and mobile were poor. It was Wild West, full of bugs and hidden secrets. Most games targeted Windows, where at some point DirectX 10 was miles ahead of OpenGL. This is one of Chronos Group members writing about the problem, and yeah, the nightmare it turned out to be to support OpenGL port for web. So the 3D graphics landscape changed. In 2014, Apple released Metal. It's not OpenGL compatible. It's completely new API for a GPU. And then the new version of DirectX 3D was released by Microsoft that promised a very high level of performance. And then Vulkan by Chronos Group that is mostly used in Android's very low-level API. So new GPUs now are being built for these consumers, for big consumers, consoles, Androids, Windows, etc. And OpenGL is getting somewhere, is getting deprecated. It's just not actual anymore. So we need a new API to be compatible with this new GPUs and new standards. Why not just Web DirectX, for example? Oh, the problem is all these APIs, they have some interference. There is an area where the surface intersects, but in fact, they are not compatible to each other. They are new, this is a new generation built on similar principles, but they are not compatible at all. There is some areas they intersect, and this is the area where the GPU was born and is trying to fit in. And this is the main goal for WebGPU, to be a universal way of talking to these new APIs, and be in this universal way your application, your code is reaching these APIs, which is quite challenging because, as I said, they're quite different. Another reason for having WebGPU are computations, GPU computations. There was a forward by Intel to add computations functionality to WebGL, but it didn't work out. So it basically was considered cheaper to start everything from scratch because WebGL was not designed for that, and it was not that much. Say the alliance behind this idea was not that big. Why WebGPU is there? WebGL is not compatible with modern graphics APIs. WebGL state machine is verbose and new APIs can have less commands. WebGL doesn't have API for computational shaders. It's not possible to fix all problems above keeping WebGL backwards compatibility. History. Since 2016, Google was developing WebGL NXT. So this is a basement for the standard. Then Apple started the WebGPU working group, and Intel was very interested in computational shaders. This is a really bright collaboration of different biggest brands in the industry, even some alternative like Firefox. I think Firefox already have a WebGPU support, experimental support. So the collaboration is quite good, and the effort is, for some features of the web platform, the effort is very sparse, and companies are trying to achieve something, different goals, and have some hidden agenda, but it's not the case with WebGPU. Everyone is really interested, and this is very promising and very very cool. Yeah, if you know this engine Babylon.js, this is an engine from Microsoft. This is already 3 years investing heavily into having WebGPU support. Right now, Babylon is #1 engine if you want to try WebGPU and don't want to go low level. They have done it really well. They rewritten half of the engine, so if you put the flag WebGPU on, it's basically another engine working for you. But they started back in 2019, the first support was there. 3JS is making significantly worse. The experimental support is there since 2020, but there is no stable group of people who work on that, and it's not even production ready, but I would not even say you can build some great experiences with 3JS and WebGPU. While 3JS is an amazing ecosystem, but it's sometimes lagging behind because it doesn't have this focused investment as Babylon.js has, because they have money from Microsoft. Yeah, right now you can try it in Chrome. It is behind the flag, and I think it's Firefox is also there. It is now in trials. After the trials are over, it's going to be planned for release. So this is like, it's sometime being postponed. There were some cases that affected postponement, but in the next 2 or 3 years, you may expect regular users to be using WebGPU. And how WebGPU API is different? How is it different low level for developers? I'm not going to go into much details, but the idea is that WebGPU is more expensive during initialization, but it's cheaper on every frame when drawing things. And it's more declarative. So you declare a thing, you initialize things, and then you just reuse them. So this is a cool example of context initialization. While WebGL on the left, WebGPU on the right. So WebGPU is a bit more verbose, it's more explicit, but not during the rendering. So this is really important because this is what's happening on every frame, and you probably know that we are trying to draw 60 frames per second, and then with new displays, I think we can draw 144 frames per second or something like that. That's crazy. So yeah, this is the code that draws, I think it was a textured triangle. Textured triangle every frame for WebGL, and this is for WebGPU. Whoever used raw WebGL? 1, 2, 3. So yeah, the point is 99% of developers will never use the WebGPU itself, like on a lower level. And the whole functionality is going to be abstracted behind engines until you are doing computations. I think the computations is quite okay to do in a raw API. There is not that much to be added. And this is one of the reasons why WebGPU required a new shaders language. First of all, the incompatibility. So they try to make a portable shaders language, very explicit, very convertible. And the idea was to go with PRV in a binary format. Then it was still big discussion about should it be binary, because binary is very optimal and has less compilations required, compilation steps, but then it was pushed for a text format. So the new language appeared, and if you ever were doing this GLSL workshops or GLSL shaders, this cool stuff, then you might get a bit disappointed because this language is different. You still, so yeah, there are a couple of reasons why WebGL is there. So the biggest one is need for separation of textures and samplers for computations, need for multiple entry points in shader, and then higher portability. So the difference in shader language is quite there. As I said, it's more explicit. The WebGL is more explicit, and to me, it's way less elegant than the GLSL. GLSL was a beautiful language, and here we see something like having a, say, aroma of machine code or meta programming. But yeah, this is for the reason to make it more portable and more explicit. Good part is that we can write GLSL and compile it on the fly to WebGL. Okay. How WebGPU is better than WebGL? This is probably the most pragmatic point. Oh, first of all, WebGPU makes less calls on every frame. We heard that before, and I've been showing a comparison of listings. So, yeah, we've seen that, this listing. And you should also understand that WebGL command, it's not directly sent to OpenGL. There is some bridging mechanism in between them. And it actually, so it was a big problem when we've been developing this operation system with JavaScript and WebGL for this limited hardware. The problem was that OpenGL is quick. Like if you run OpenGL performance test, it's super quick, good enough for us. But then when we move everything to browsers, there is a bridge in between of OpenGL drivers, and the JavaScript commands we execute in V8. And this bridge was eating the sending command from a browser to OpenGL driver was taking quite some time. And there are many of these commands for a WebGL. So the problem is not only WebGL is sending many commands, they're being sent through the bridge. So it makes any web API trying to talk to drivers, to graphics drivers, a bit slower than you'd expect that, or you have it in a native system. But also, WebGPU commands are cheaper. Just it's less of them, but they are also significantly cheaper, for the reason that you may think it's a similar picture. So WebGL command goes through the bridge, WebGPU command goes through the bridge, but it's not really true. So the scary fact is that WebGL, it is designed to talk to OpenGL, but it doesn't talk to OpenGL anymore because many systems doesn't have OpenGL support anymore because OpenGL is getting deprecated. So what happens actually on this laptop, WebGL talks to some intermediate layer. So you've seen this list of commands, like 50 commands every frame. They don't go to GPU driver directly, they go through the bridge, but they also go through the angle interpreter that can actually convert them to the command that is suitable for Metal, for this MacBook. This is quite a number of layers of operation, right? And you make it 60 frames per second, 50, 60 commands. This adds a lot of overhead. While for WebGPU, the compatibility with new APIs is so good that these commands you send every frame, they are often just mappable one-to-one. So the interpreter is not required, or it is required way less, and it's very simple mappings. While the bridging of drivers are still there. Yeah, so it is less commands, and they are not interpreted. There is some performance problem, promise in that. Another very important thing is it is designed to be pre-initialized, so there is less of shaders recompilation in a runtime. Many times, I don't know how many of you work with computer graphics, but I mean, being fans of a graphic, of a smooth experiences, thanks, man. But you may find that WebGL is never very smooth. Like even at around 60 FPS, it feels like it never feels like a AAA game, or it never feels like a nice 3D benchmark which runs at a full speed. For the reason that there are many processes that block execution, and one of them is shader recompilation. It is like a garbage collection for a JavaScript, then a shaders recompilation is for GPU processes. So WebGPU promise is no shaders recompilation. So web applications, web 3D applications can be as smooth as native applications are. Oh, WebGPU performance summary. WebGPU designed to have less calls per frame. These calls are cheaper, and unexpected shaders recompilation are avoided. So the promise is it's going to be faster. Okay, we should be having some demos. So yeah. This are Babylon.js demos of a very densely populated forest. And this is a WebGL version which runs at 40 something FPS, while the stage is not very advanced, and WebGL is now very high. It's highly optimized now. There are many techniques to optimize that used in this demo, but still the FPS drops, and there is no animation also. Still FPS drops to 40, 45 from 60. This is a WebGPU version. Well, it doesn't. It's not impacted by the drop of FPS for the reason that on every frame, all these trees they're pre-initialized, and on every frame, these commands or these pipelines are being just reused. So it's just cheaper. Drawing many things is significantly cheaper. There is a video, but not sure we need it. So yeah, that's a big promise. Less commands, cheaper commands, more FPS, smoother. I tried to recreate the demo, but just did something on my own to check, to double check, because sometimes people, because Babylon.js is an engine, and they always try to be, hey, we are so quick, we are so fast, like, and they sometimes like tune the demos. So I made another one. And I've been doing it quite a couple of times during the last year. So the first time I tried, surprisingly, WebGPU was 30% slower. And I wrote to people, and what happens? Why WebGPU is slower? and said, well, it's not ready yet. We're still optimizing, and WebGL is already quite good, quite optimized. So, well, this is WebGL 237 FPS, and this is year after they got it to work with WebGPU being approximately 10%, 20% faster than WebGL. So it's improving. Like if you look 1 year ago, the WebGPU was slower. Now it's 10% faster. It can be even more faster. But it will never be twice or triple faster than WebGL. So even technically the improvement is incredible, and it's way more optimized, you will never get something revolutionary, more performance than WebGL is. It's going to be significantly smoother, 30% faster, and getting less battery from your application. It's keeping your user with more power for longer, but yeah, so WebGPU performance is improving, but it promise a lot of improvements, but it will never be a revolution. What's going to be a revolution is the GPU computations. You may say WebGL, we heard it many times that you can do some calculations on WebGL, like this TensorFlow.js and some fancy things. Mostly neural networks doing or mining crypto, doing calculations on WebGL. This is possible, but this is a hack. How this hack works? In WebGL, you can run fragment shader. What fragment shader is, you create a canvas, basically, and for each pixel on the canvas, you can run a program on GPU. So you run a program, you send some data in there, you set a color of pixel, for example, and write a program that has a return as values of pixels. You can't read this data from the buffer directly. You need to read them from this canvas, from pixels. And you need to read them with getPixels data, which is a canvas API from JavaScript. How can GPU parallel computation efficiently happening with getPixels data? This is a bit, yeah, this is a hack. And WebGL was never designed for that. It is also done in a synchronous way, which is very important. So once you do WebGL computation, it blocks everything. You need to draw on this canvas, you need to read from canvas. This is asynchronous, and it creates a lot of limitations. While WebGPU compute, it is asynchronous, it doesn't block main thread, it reads from the memory directly, and well, it's just quicker. I made a benchmark which is based on matrix computations, which is a popular benchmark for parallel computations, and not only. So the JavaScript died very quickly. So this is the size of a matrix, and this is the y-axis is for time spent. So the JavaScript died like 700 something matrix. This was a limit, and WebGL was doing more or less well, but then on 3000, because you have a limit of how big your canvas can be. There is a physical limit that it can be only 4000 pixels or something. And then the WebGPU was just keep going. It was 3 times more performant than WebGL. So this is where the revolution is coming. Now browser can efficiently use GPU to make calculations, and this is what may open door to new kinds of applications. For example, video editing, or audio editing, or different physical emulations. This is what to expect. Oh, you know, this video editing, I think, is going to be one of the biggest applications for this. Also, machine learning in browser, image recognition, and a client. Oh, better graphics, of course, because now we can not just do smoother graphics with less WebGPU commands, but we can also unload some graphical problems to GPU completely and do it in a synchronous way, not load in the main thread. For example, characters animation can be now done on GPU instead of doing this in JavaScript. And this empowers us with more tooling for graphics. And the synchronous nature of these computational shaders makes possible some really, really great things. Well, I have this video.
Some time ago, I read an article about ocean wave simulation in the movies Titanic and Waterworld by Jerry Tessendorf. Their approach has become a standard for rendering ocean surface in film and is often used even in video games. It has two key components: fast Fourier transform and oceanographic spectra. In this video, I'm going to walk you through the basics of this technique and its implementation in Unity.
So the challenge is how you make realistic waves and waves with some physical emulations that look good enough for Titanic or some AAA game. And so where do I have it? And before WebGPU compute, it was not possible to do on the web because you need a way to compute in a synchronous way, not load in the main thread, and you need to make millions of these computations for every point of ocean. So this is a very accurate physical model of ocean, which is calculated on GPU at 60 frames per second. So it doesn't load the main thread. This was not possible before. And there are many interesting tricks applied. So for example, this probe, it is lagging behind a bit because you need to send data to JavaScript from WebGPU, and it's lagging by 100, 200 milliseconds behind the wave. Because the wave itself lives totally on GPU, so it doesn't exist. All these coordinates doesn't exist by default in JavaScript world. You need to download them as a buffer. So this is what's really new. The computations that give us ability to use the power of GPU as it should be. Well, of course, crypto mining will be faster. So WebGPU could be treated as WebGL 3, but breaking API syntax plus computations. The need for it came from the fact that contemporary graphics API are different from OpenGL. WebGPU promises performance improvement while it's not revolutionary, rather some smoothness upgrade. The brand new feature is WebGPU compute shader that allows to unload CPU and make async computations on GPU in an efficient manner. We can expect further performance improvements, still in progress. New kinds of apps built on the web with WebGPU. While you may never see the difference because it's going to be abstracted behind engines, while new kinds of applications could appear on the web. That's pretty much it. Thank you for listening.